The functions on the calculator to get you, or the buttons that you press on the calculator to get you to the absolute value function would be alpha, window 1, or math num1. All right. So if I just wanted to find a simple absolute value of a number, like -5, for example, I would hit alpha, window, enter. I did not size this up the way I wanted it to. All right, we'll just bear with it for now. Make it a little smaller. There we go. -5, for example, and it'll just spit out the absolute value. So if you want to create a graph, you go to y equals, you type in the function, but now we know where to find the absolute value function. All right, so let's say we're looking at number 1. I want the absolute value of x minus 2 minus 4. So alpha, window, option 1, x minus 2, hit the right arrow to get out of the brackets, then minus 4. All right, so now we have our equation in there. And you can look at the picture just with a quick zoom 6, standard zoom. You see it looks essentially like what we have here. It looks exactly the same, but it looks close enough. You know, it's a little offset to the right, and you know, we got pretty much everything we need. So if we wanted to do that process again for another graph, we could. So we'll talk more about that as we go forward. I do have my graphing calculators back from the AP exam, so if you need to borrow, they're in the drawer, so they're ready to rock and roll. But I wanted to show you how you write the equation of an absolute value function from its graph, and then I wanted to talk to you about piecewise functions. So starting with number 4, you got to identify 2 pieces of important information to create the equation. 1, the vertex. 2, the slope. Right? Specifically the slope to the right of the vertex. Corresponds with the vertex, so we now know that information. We just need the slope, specifically the slope to the right of the vertex. So I'm just going to grab any convenient point to the right of that vertex and use that to compute the slope. It doesn't matter what point you select as long as it's convenient. So this one has a nice convenient point 1 unit to the right. All right, so I'll take that. So down 1, right 1, down 1, right 1. So the slope is going to be equal to -1 over 1, which is -1. That's the a value. So we have the a, we have the h, we have the k, which means we have everything we need to write the equation. All right. So I'm going to say we have f of x is equal to a absolute x minus h, close it up, plus k. And I'm going to replace the a with a -1, the h with a 0, and the k also with a 0. Now, if you want to simplify this a little bit, you can, but it's not necessary. Right? It's in a nice vertex form. It's properly formatted. But, you know, for the sake, bless you, of a multiple choice question, maybe you're looking at something that, you know, one of the choices is the simplified form of this, and this is not one of the choices. You got to be careful. So this could also be written as negative the absolute value of x. All right. So we could have also gotten this equation based off of its relationship to the parent function. So this is just a direct reflection of the parent function absolute value of x. Right? Its vertex didn't change, the slope didn't change, just its orientation changed. So knowing that, we could have just flipped the sign of the a value and been done with it. Right? So if you pick up on little things like that, that's a good thing. Right? Somebody along the lines asked me, and I answered that one person. I didn't mention it to everyone, and we hadn't talked about it in a while, so I figured I'd bring it up now. when you see something like g of x, that's really saying the same thing as f of x. It's just giving it a different name. So f of x is our first way of denoting a function of x. But then when we want to distinguish another function from that function, we call it something else. Instead of using subscripts like f with a little subscript of 1 of x, f with a little subscript of 2, and so on, we say f of x, g of x, h of x, and work our way down the alphabet from there. Right? So when you see g of x, it's really just saying a function of x. Right? So we could also write this as g of x is equal to a times the absolute x minus h plus k. All right. Identify the vertex. That's nice and easy. -2 is 0. The -2 is the h. The 0 is the k. I need the slope, but specifically the slope to the right along the graph. So I'm going to find the next convenient point beyond the vertex going to the right. All right, so that's one that crosses at a recognizable location. So this one looks pretty good. It looks like I have a +2, +1. So my slope is equal to 2 over 1, which is 2. Again, that's the a value. All right. So my equation would be 2 absolute x minus, the minus is built in, x minus a -2 plus 0. You can skip that one step and just write it as 2 absolute x plus 2 plus 0, or just leave off the plus 0. That's fine also. All right. So not too bad. You know, like you can pull that information from the graph pretty easily. What we're going to do is switch to the packet now. Hang on to that sheet because that's going to be part of your assignment. But we're going to learn about piecewise functions. All right, so that's page 5. And at the top, there should have been some space for notes there, so I'll take that as a typo. It's the piecewise definition should have been given, or space for it anyway. All right. So the piecewise definition, a piecewise function is a function containing two or more pieces plotted on the same set of axes. A piecewise function is a function containing two or more pieces plotted on the same set of axes. Little formatting issue with page 5 also. Number 10 should actually come after numbers 11 and 12. So take that as a typo also. So long story short, we're going to go to number 11, do number 12, and then we'll come back to number 10. All right. But when you look at the structure of these functions, they look pretty beefy. Look like they have a lot going on. They're really not as complicated as they seem. And they seem pretty complicated, so that's not really saying much. But if you look at it as two separate equations that are being graphed, but only parts of those separate equations on the same set of axes, then you're in a good spot, because that's the way you should be thinking about it. So what this is really interpreted as is f of x is equal to 2x plus 4. But sometimes f of x is equal to 6 minus x. It's just what constitutes the sometimes. Right? It's saying that it's 2x plus 4 under these circumstances, when x is between -4 and +1. It's 6 minus x only under these circumstances, going from 1 to 5. So what I would do is make a table of values. Well, there's one way to do it. F against f of x. X against f of x is what I meant to say. The x values that make up that table would be the x values that they're telling you make up the restriction, saying it goes from -4 to +1. So -4, -3, -2, -1, 0, and +1. For the other function, or the other piece to this function, it's going from 1 to 5. So x, f of x, 1, 2, 3, 4, 5. I just need some y values to go along with those x values. And yeah, you're not limited. I mean, you could use your calculator if you want. You can do it in your head.
Wouldn't it not be 1 because it's not greater than or equal to?
You're right, but we still include it. We just include it with an open circle on the graph. Very good. So what we're looking at are two linear equations, and those linear equations have a constant rate of change. So I could go to a calculator here, but I could also just figure out the first one and just know that the slope is 2. All right? So if I take, let's say, for example, a -4, that would be the first one, plug it in for x here. All right? Plug in the -4 for x. I'll get a -8. -8 plus 4 is -4. I could do the same thing with a -3, -2, -1, 0, and 1, but that's too much effort. Right? If the slope is 2, a +2 specifically, it means that the difference between consecutive values in the y column has to be equal to 2. Meaning, to get from one value to the next value, just add 2. All right? So the next one would be -2, then 0, then 2, then 4, then 6. You could also type it into a calculator and go to the table of values to get the points, but you know, it's efficient. Efficiency is what we're looking for. All right, for the other one, same deal. Start off with the 1 and plug it in, but really this one's a whole lot simpler, because I'm taking 6 and subtracting from it each one of the numbers in the x column. 6 minus 1, 6 minus 2, 6 minus 3, and so on. Those are pretty easy computations. All right, so 5, 4, 3, 2, 1. All right. So I would plot all these points. The exception is this one is going to get an open circle. All right, this ordered pair is going to get an open circle because it involves a less than symbol. All right, less than symbols, greater than symbols get open circles. All right, and that goes back to what we were doing with inequalities back in, I think it was November, October. All right, open circles whenever you're greater than or less than, because you can get really, really close to that number, you just can't actually get there. right? So if I said that, I'll keep it simplistic, like I'm over 40 years old. If somebody said, oh, I'm going to guess that you're 42 years old. I'm going to guess that you're 70 years old. And I'll be like, that's nice of you. But somebody's like, I'm going to guess that you're 40 years old and 1 second. Like you're all right. Like anything that's beyond the 40. But if somebody said, I'm going to guess you're 40, well, now you're wrong. All right? 40 years and 1 nanosecond. You're still right. You're very close to that number, but you're not actually there. So what we do is we represent that location with an open circle, knowing that you can get really close to that location, but you can never actually get there. All right, so we plot -4, -4, -3, -2, -2, 0, -1, 2, 0, 4, 1, 6. These are all good points, solid points. But then at 1, 5, we plot an open circle. The rest of the points are all solid points. So 2, 4, 3, 3, 5, 2, 4, 2, and 5, 1. And that would be your piecewise function. Now, if you're dealing with two complete equations, you'd have a line that went all the way up like this and a line that went all the way like that. It would have been a system of equations. What they're saying here is just take a fragment of one equation, take a fragment of the other equation, and put them together in the same graph. And there are a lot of different applications of stuff like this. And you just think of any object that's in motion that follows a certain path for a certain period of time and then changes the path that it follows. Not everything is just going to be a parabola. Maybe it follows a parabola and then it takes off in a horizontal line. So there's a lot of different applications. A lot of different ways to graph these things too, right? Like we just did it with a table of values approach. But you could also do it like, a second ago I just demonstrated you could graph the whole line, but that would be a waste, all right? But what you could do is start thinking about what the entire line would look like on the graph and just get rid of the parts that you don't need. So if I'm looking at the second one, h of x is sometimes equal to -2x minus 6, and some other times it's equal to 1/2 x minus 6. I could handle this by saying, all right, well, what would it look like if I graphed the whole thing? I'm going to go back to the blue and red. Should have done that initially. So it would have a y-intercept of -6. And a slope of -2. All right, so I'm not going to do this with table of values. I'm just going to look at it like, all right, this is what it's going to look like. 1, 2, 3, 4, 5, 6. A slope of -2 would be down 2, right 1, down 2, right 1. It would also go the other way. I'd have all these points. Now I have the benefit of using digital ink here, so I could easily wipe out the points that I'm plotting. If you do this in pen, you're going to pay a price because we don't need all these points. All right, so you want to think about the points that you actually do need. All right, so this is saying I only want the points that are less than a -1. Only points less than -1 on the x-axis. All right, so here's -1 on the x-axis. I don't want to go to the right of those points. I don't even want to get to that point. All right, so all of these are fine. These have to go. All right, so anything along this line, this vertical here, would constitute the boundary. All right, so I can get to that vertical, but I can't make contact with it, and it's an electric fence. Right, not the dog one, but the one like the electrified fence where if you touch it, you get zapped. Like, you know where the fence is, you're not going to touch it though. All right, so I'm going to put an open circle there to say that's the point that I can get close to, but I'm never going to actually touch it. All right, I can't take any of the points on the other side, but I can get every one of these other points here. Now, because it says I can be less than -1, it doesn't restrict how much less than -1 I can be. It could be -100,000. I could be -1,000,000. I could be -infinity. So I put a set of arrows on this, or I just put an arrow on it is what I should say. Arrowhead. All right. The other way, y-intercept is still -6, so I'd start off at -6. 1, 2, 3, 4, 5, 6. My slope is 1/2, so up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2. But then I look at my restriction, only points to the right or greater than or equal to, only points more than or equal to 2 on the x-axis. So here's 2. Anything along this vertical is fine. Anything to the right is fine. Anything to the left would be out. So I would take any of these points, include them. That's part of my line. It goes on forever because it could go greater than 2. It could mean anything. It could mean 100 million. It could mean 10. You know, a lot of different possibilities. There's no restriction to it. All right. But that y-intercept has to go. Now it begs the question: why did I put it there to begin with? You know, I look at it like, well, I had to figure out where to start. If I'm going to plot the points, where do I start my graph? I have a slope, I have a y-intercept. I'll start with my y-intercept, but sometimes I don't need my y-intercept. So after the fact, I get rid of it, but I don't know to get rid of it until after I've accounted for the domain. All right, so the greater than, the less than stuff. All right, so that's an alternative approach. You could still do, you could do number 11 with the approach that we just used, and you could do number 12 with the table of values approach. It's really up to you. It's just a question of what you're more comfortable with, right? But in either instance, you have to take into account the domain. All right.